tutorial we will discuss Brownian motion. In earlier lectures, we have seen the diffusion of the let's say gas molecules or a dye in a liquid or in a gas. So in that case, particle size is of the order of nanometers. Okay, but in this case we will discuss what if there are some bigger molecules of the order of micron size in the fluid or in the nanometer size particles. Okay, so these are some bigger particles inside the gas or inside the nanometer size particles. Okay, so in the last lecture we have seen that the diffusion equation is a stochastic process or it's a random walk problem. It can be understood well from a random walk problem. In that case, if let's say x is the particle distance or displacement, x is the particle displacement after time t, then we have seen that the average of x is 0, the x square value is proportional to or is equals to n l square, or let's say not in terms of l, in terms of time, this is l v bar t. L is the mean free path and v is the mean or average velocity, and t is the time. So we have started. So let's say we put some dye molecules at t is equals to 0. So initially the distribution was the delta function. We have already seen that the density will follow this kind of equation, grad square n d, where d is the diffusion coefficient, and it will, and the probability density function due to the central limit theorem was ptx 1 over 2 pi l v bar t exponential minus x square by 2 l pt. So particle started at t is equals to 0 with a delta function. Okay, then slowly with time it spreads out. So the width of the delta function increases and it spreads out, and eventually, so from this equation we can see that the diffusion will stop when there will be no gradient in n present. So the in equilibrium everything will be uniform. So the dye molecules will be uniformly distributed among the fluid particles, and the dye molecule size is actually of the order of same as the fluid particles. Now what if we ask that what is this is for the displacement a random variable. If we consider the random variable velocity, okay, this velocity, average velocity, let's say, so the velocity same as the displacement, one can say that since the particles are confined and overall they are not moving, they are not going anywhere. So if let's say v is the for 1D, let's say we are considering one component v in any direction. P is the velocity of the particles. Then obviously mean velocity will be 0, and again the root or mean square velocity from the, since we are considering the thermal equilibrium, one can say that this mean square velocity or their kinetic energy will be kBt. Okay, because eventually they are colliding with the walls and they are exchanging energy or getting energy from the walls and equilibrium. They are in equilibrium, so their average kinetic energy is of the order of the thermal energy present. So this one can derive from the kinetic theory of gases in equilibrium. And this is same as that V bar. This, so in there we denoted with overhead bar. So half mv square, it will be kBt. So what will be the distribution of the velocity then? So the particle, let's say, started with some velocity v0 and it start moving and doing all kinds of random motion, and then we are asking that what is the mean square velocity. So again from the central limit theorem we can say that the velocity will also follow Gaussian distribution. Then the velocity PDF will be time, let's say t, since it has no time dependence in this case, we are already considering the equilibrium state. So in that case probability density function PV will be 1 over 2 pi kBt. Oh, so it's of the order of 1 by 2 actually, so 1 by 2 cancels out. 2 pi kBt over m e to the power minus 1 minus v square by 2 sigma square. So sigma is, for our case, sigma square is kBt by m. So m v square by 2 kBt. Okay. For 3-dimensional case, this is simply m over 2 pi kBt. All components will add up, 3 by 2 exponential m v square 2 kBt, and in here v square is the v square plus vy square plus vz square. So in equilibrium situation, the particles are uniformly distributed inside the volume, so their probability to present at any point is actually proportional to the volume. So the total probability of the phase space to have a value, okay, so the notion of phase space is that we have a 6-dimensional, or we have coordinates and velocity space. So it's a 6-dimensional space. So I'm not going into the detail, but let's say if you want to know that what is the probability of finding the particle at any position r and v, then it will be simply 1 over v, because particles are uniformly distributed. So v is the volume of the container, and the velocity will follow Gaussian distribution, but this is actually called as the Maxwellian distribution. Okay, so let me write it properly. Maxwellian distribution. One can derive this from the kinetic theory of gases also, and from the central limit theorem also. It is obvious. Maxwellian velocity distribution. Okay, so this one 2 pi kbt 3 by 2 e to the power minus half mv square by kbt. Now we are asking that what if between these nano sized particles there are some micron sized particles present. So what will be their equilibrium probability distribution, what will be the diffusion coefficient for them, etc. So how to answer this question? In previous case we have chosen our random variable. For the displacement vector is the x, for velocity is v, and we somehow from the random walk problem derived the root mean square or the standard deviation from the random variable, and then from that, for applying the central limit theorem, we have derived the probability distribution function. In our case, how to proceed? So the best way is to write the equation of motion of the particles, because we are considering that the particles density is not high enough, so they are not interacting with each other, but they are interacting with the fluid. So let's say this is the Brownian particle and it is present inside the fluid. So fluids are doing all random motion. Okay, so let me tell you the background story of the Brownian motion. So Robert Brown in 1827, so he was a botanist, collected some pollen grain and he crushed them those grains. So if you have seen some hibiscus flower, so it has some grains in the flower. It is clearly visible, one can see. So he collected some pollen grain and put it in a petri dish in water. Next day he observed that the grains are quite spread out and he thought that they may be alive. But the root cause was not that they are alive, but they went random walk due to the random collisions with the fluid particles. So there are tiny, so this is the big particle and there are tiny fluid particles are present, and they can hit them, these big particles, randomly. Okay, anyway, and this is like they are hitting it randomly, and due to this random energy or the random collision, these big particles actually move. So we are asking the question that what is the diffusion of the particles due to the random collisions within the fluid molecules. Okay, so our approach is to first write the equation of motion for the Brownian particle. So one more, so the assumptions, okay, so this is Robert Brown 1827. So the assumptions are that the mass of the particle, Brownian particle, is much greater than the mass of the atoms. Also, one more assumption is that the bigger particle, the Brownian particle is also in thermal equilibrium with the fluid particle. Fluid particles are itself in thermal equilibrium and the big particles are also in thermal equilibrium with the fluid particles. Okay. Now let us write the equation of motion. So if m is the mass of the particle, then mv dot will be, and the motion is due to the random force of the small particles. So let's say this is some random force eta t. Now we don't know exactly what is the form of eta t, because it is purely stochastic process. It is not deterministic. Let's say the particle at time t has an average or let's say a random force is eta t. At some other moment it is different and it is uncorrelated. What is the previous time, what is the noise or the random force. So this is the random force which we can't predict what is the form of it exactly, or noise. We don't know its exact expression. So we do not know its exact expression. Now let us integrate this equation. So now let us integrate this equation. Okay, so this is m dv by dt is equals to eta t. So m, let's say m is here, so vt minus v0 is equals to 1 over m eta t. Now v0 is the initial velocity of the particle which we are tracking. Initial velocity of the Brownian particle. So now, okay, why we are starting with the equation of motion, it will be become clear later, because it is easy to get the velocity correlation first, and from that one can derive the displacement or the for displacement vectors as well. So okay, and there is I missed one thing. Okay, yeah, integration over 0 to t eta t dt. Okay, if let's say the initial time is 0, t0 is 0, so there are, now we have to average this v. So how can we average it? Now since we have chosen one particle and it has some initial velocity and it has some random force, but as time elapses the random force rapidly changes. Yeah, so there can be many realization of a single random force. So one way is to have a given condition v0 and average over the all realization of the random noise. So let us do it. So let us denote it by overhead bar. Vt is equals to v0. V0 is a constant, so the average will be the same, 1 over m 0 to t eta t dt and average. But since this force is completely random, so average over all realization or initial condition is actually 0. The first moment of this equation is 0. Now we are left with two things. So we have Vt bar is equals to V0, and now let us do the average over the all initial condition. Okay, plus one over m, this part is 0, so V0 averaging, and since we know what is the equilibrium probability density function, because we have already considered that the Brownian particles are also in thermal equilibrium with the fluid particles. So this average velocity, so average will be like this, minus infinity to infinity dv0 v0 and p having position, let's say some r, and v0, okay, dv0. This is the average over all initial velocities. But since this is a symmetric function and this integration is odd under v, so the integration will also go to 0. So vt bar average is 0, which is obvious because the mean velocity is essentially 0. Now let us do the mean square velocity, because if the mean velocity is 0, one has to rely on the mean square velocity for the order of magnitude. Okay, so let us do it. So again, for this case also, we have started with a delta function. At t is equals to 0, we have the particle velocity, some v is equals to v naught, and then we are looking at the distribution function or moments of the display of the random variable, which is velocity here. So earlier it has started with the delta function, but now with time it converts to a t is equals to infinity, it converts to a Gaussian distribution. Now let us calculate the mean square velocity. So v square t will be v0 square plus 2 by m v0 0 to t eta t dt plus 1 over n square 0 to t dt 1 0 to t dt 2 and eta 1 eta at t1 eta at t2. Okay, now let us average over the all realization of the noise. So v0 is constant, so average will not affect it, and here average over eta and average over this. So the noise is totally random, right? And also this, the effect of noise at one instant is independent of the effect of noise or the noise at other time. So we can immediately say that this correlation, so this average over all realization is essentially equal to the average over all initial conditions, and which is nothing but some strength times delta correlated in time, because we are saying that at t1 is equals to t2 they are related. Apart from that they are unrelated. They don't depend on the noise at one time, doesn't depend on the noise at next time or any other time. Okay, and this is some constant, because the delta function has the dimension of we have seen, right? So the delta function has a dimension of, in this case it has a dimension of 1 over time. This has a dimension, this has a dimension of velocity square. So this gamma has a dimension of the order of diffusion constant, so it has L square t. Okay, so this is the strength of the noise, and since this is the noise which is acting on the Brownian particle, so it may depend on the properties of the Brownian particle. We will see as we go along. Okay, so these kind of noise, and these are also totally random variables, independent random variables. So their distribution will also be a Gaussian distribution, and so this kind of noise is actually known as the Gaussian white noise. In general, this is known as Gaussian white noise. Okay. Now let us put this back into the above equation. So v square t is v0 square plus this part is 0. This is 0 because the noise of all average over all realization or all initial condition is actually 0. Initial condition of the noise, not the velocities. Okay, the velocity average we will do next. So second term is 0 and the third term is 1 over m square 0 to t dt1, and you know that the delta function property, right? So f of x delta x minus infinity to infinity is 1, or if let's say it has delta x minus a fx integration, then this is f of a. So no, not 1, f of 0. So we will use this property, and since the function here, okay, let me put first 0 to 2 dt2 gamma delta t1 minus t2. Since there is nothing to put and we are integrating over d2 dt t2 variable, so we will put nothing to put actually. So if let's say there is some function of f t2, so in place of t2 we have to substitute t1. So this will be v0 square gamma over m square 0 to t dt1, and this is t. v0 square gamma over m square t v square t. If you average over the all initial conditions, so there is nothing to average, so this will be v0 square, which is kBt by m in thermal equilibrium situation, plus gamma t over m v square t. But we have seen, since the particle is in thermal equilibrium, the root mean square value does not depend on time, but this time this is increasing with time. So there is some problem, and the problem is that since the particles are heated by the small tiny molecules of the medium, so it moves, right? And as it moves, there is certain kind of drag. So whenever you move in rain, so you feel some force, right, when you move forward. So there are more particles which hit you from the front side, so there is a drag. Okay, so let's say there a heavy wind is blowing and you move in the wind, so you feel some kind of drag. So that drag is missing in our equation. So the equation of motion which we wrote has to have a drag. So dv dt m dv dt is equal to some drag, which is proportional to obviously velocity, because if you move fast you will feel more force as if you have moved slow. So mv, okay, constant, which is, it's a gamma, small gamma, v plus eta t. So this equation is actually correct. So this is the noise, or the from this situation we have this, it is giving us a view that the bigger particle is gaining energy from the smaller ones, and it is infinitely gaining energy, it doesn't lose anything. But this is not the physical situation, it can't gain energy at infinity long times, so there must be some kind of drag. Okay, So due to this random force, particle gains some energy, and this is the drag, and this is random noise. Both is coming from the bath, which is provided by this tiny molecules or the fluid molecules. Okay, now let us solve. Let's calculate the mean velocity and the. So this is one component of velocity. It can be a vector, but for our simplicity of our calculation, this is Vt is one component of the velocity. So let us solve it. Okay. So how to solve this kind of integration? You can do it explicitly, but just I will tell you the easy way. The integrating factor for this differential equation, integrating factor is e to the power gamma t. So if you multiply both sides, so let us pull this m down to this side, 1 over m. Okay. So if you, let's say, multiply with this e to the power gamma t, so d by dt of Vt e to the power gamma t is equals to minus gamma v e to the power gamma t plus to the power gamma t eta t over m. So take this to this side, so this will become dy dt of Vt e to the power gamma t, and this will be 1 over m eta t e to the power gamma t. Now integrate it 0 to t dt. We will have, so Vt e to the power gamma t minus at 0 time has a value v0 is equals to 1 over m integrated over 0 to t eta t e to the power. Okay, so let us put a prime here because our limit is up to t, right? So just put a prime here, eta t. Okay, e to the power gamma t prime dt prime. Okay, so this will be Vt is equals to v0 e to the power minus gamma t plus 1 over m e to the power, we can write this way, 0 to t eta t prime e to the power minus gamma t minus t prime dt prime. So now this is the equation of motion for the velocity at time, not equation of motion, it's velocity, the Brownian particle at time t. Now let us do the averages. First, the time average over the all realizations of the noise. So Vt bar will be v0 e to the power minus gamma t plus 1 over m, and this part will be simply 0 because eta t average is 0. And second, again we will have Vt bar average over all initial conditions is simply is equals to v0 average to the power minus gamma t, which is 0. Now let us do the v square t. Okay, first just write it, what is the expression of it. So it is v0 square e to the power minus 2 gamma t plus 1 over m v0 0 to t to the power minus gamma t eta t prime to the power minus gamma t minus t prime dt prime plus 1 over m square 0 to t. Okay, yeah, so eta t prime to the power minus gamma, just this, okay, dt1 0 to t dt2 eta t1 eta t2 e to the power minus gamma t minus t1 the power minus gamma t minus t2. I just use t1 t2 because otherwise you have to put double prime and prime, so these are dummy variables, doesn't affect the whole integration, so you can write in terms of t1 and t2 as well. Okay, now let us do the average over the realization of the noise. So this term will drop out, this term will not affect, and this is a delta correlated noise. So we will substitute the value of the noise correlation. It is 1 over m. Gamma will come from this part, 0 to t dt1 0 to t dt2 delta t1 minus t2 e to the power minus gamma t minus t1 e to the power minus gamma t minus t2. Okay, now substitute t is equals to t1 in place of t2. So what we will have 0 to v square e to the power minus 2 gamma t plus gamma over m 0 to t dt1, and this integration will, we are operating the delta function, so this integration will be gone and we will replace in place of t2 t1, so it will be minus 2 times t minus t1, right? Now solve it for t1. So what will you have? 0 square e to the power minus 2 gamma t, okay, there is m square, sorry, yeah, gamma over m square to the power minus 2 gamma t is doesn't affected by the integration, so 1 minus 2 gamma will be pulled down e to the power minus, okay, plus gamma t e to the power 2 gamma t1 minus t1, okay, t minus 1. So finally b0 square e to the power minus 2 gamma t plus gamma over m square e to the power, okay, minus 1 over 2 gamma to the power minus 2 gamma, it will be 1 minus e to the power minus 2 gamma t. Okay, so if you put common, take common, so what will you have? I think I did some mistake, there will not be a minus sign because this t1 is actually plus. Okay, so this is plus, so v0 square minus gamma over 2 small gamma m square and common e to the power minus 2 gamma t plus gamma over 2 gamma m square v square t whole average. Okay, not whole average, it is the average over the all realization of the noise. But if you do the average over all initial conditions, then also you will have this v0 square will then be kBt by m minus gamma over 2 small gamma m square e to the power minus 2 gamma t plus gamma 2 gamma m square, right? Now you expect that there should not be any time dependence, right? But this is coming. So we have already assumed that our Brownian particle is in thermal equilibrium, so there should not be any time dependence, so this term must be 0, right? So kBt must be equal to 2 kBt gamma m, or gamma must be equal to, the strength of the noise must be equal to 2 times kBt 2m kBt 2m kBt. Oh, there is small gamma also, so 2m gamma kBt. So what you have seen, what we obtain now, we obtain that the strength of the noise is proportional or is equals to 2m gamma kBt. So what does it include? This is actually the drag term, right? The drag the particle feels. So the noise and drag are actually related, and this relation is known as the fluctuation dissipation relation. Fluctuation, so this noise is actually like fluctuation, and this gamma is like dissipation relation. This is a very important result, which says that if the particles hit more rapidly, then there will be more drag because it will move faster, so the drag will be higher. So drag and the noise are actually related, and we will see this drag gamma is actually, since this drag is due to the fluid particles, so it has to be related to the fluid viscosity. What is the relation? We will see. So till now what we have done, so we took one particle and done and see write its equation of motion and did the average of the velocity over the realization of realization over the noise, and then realization of the all initial conditions, and we now have the expression for the root mean square velocity, and from that we obtain a important result which relates the strength of the noise to the drag term, and that relation is the fluctuation dissipation relation. But remember that the whole system is in thermal equilibrium. Okay, the Brownian particle is in thermal equilibrium with the bath, and bath is already equilibrated. It is making all kind of random motion, hitting the walls, and the overall system is at thermal equilibrium. But it doesn't mean that there should not be any time dependence. There can be time dependence, but the average quantities doesn't depend on the time. Okay, so this is so there can be a motion. Let's say equilibrium doesn't mean that everything is still, nothing is time dependent. There is time dependence, but the time dependence doesn't appear over the average quantities. Okay, so that is the main significance of the equilibrium. Okay, now okay, so what was our main objective? Our objective was to find the diffusion coefficient for this bigger molecules. For that we need a expression for the displacement, or for that we to have a, so last time what we did, we took our random variable as the displacement vector and we calculated its mean square or square average. But to do that directly in X is a bit tricky. So for that we have started from the velocity equation, and now from the velocity equation we will write the equation for the displacement, or we shall derive the expression for the mean square displacement. For that we shall need one more quantity, which is the velocity correlation. Till now we have derived the mean square velocity average. So Vt times Vt, right? Now what if the two times are not same but they are different? Okay, so now we will find the average value of this quantity. So this is the mean square, not mean square, this is the velocity correlation at two different times. Velocity correlation. So what is this? So let us write it. So Vt into Vt prime will be V0 e to the power minus gamma t plus 1 over m 0 to t dt, okay, prime eta t prime e to the power minus minus gamma t minus t prime times V0 e to the power minus gamma t prime. Oh, this notation is actually, so let us use 1 in place of prime because this time has one prime index. So t1 gamma t1, okay, plus 1 over m 0 to t dt2 eta t2 e to the power minus gamma t prime minus t2, and if you multiply these two expressions you will have v0 square e to the power minus gamma t plus t prime plus this linear term will vanish, gamma m square if you average over the, okay, let me write it this way, vt prime all realizations. Then what we will have? We will have 0 to t, so this is prime, dt1 0 to t prime dt2 eta t1 eta t2 will give us so gamma and delta t1 minus t2 e to the power minus gamma t minus t1 e to the power minus gamma t prime minus t2. Now let us do this integration. So v0 square to the power minus gamma t plus t prime, this one, and this one is, so since this delta function, so the limits are like this, right? In one axis we have t1, in other we have t2, and t2 is going from 0 to t prime and t1 is from 0 to t. So t1 is, this one is t1, and delta function means that t1 is equals to t2, right? So if you do the t2 integration first, So this delta function will hit only up to this point. So t1 will be up to t prime only when you operate the delta function. So this integration would be t prime t1, and substitute in place of t2 t1, so you will have to the power minus gamma t minus t1 to the power minus gamma t prime minus t1. Now integrate it. So this t1 t plus t prime will again will be out of equilibrium, v0 square to the power minus gamma t plus t prime plus gamma over m square e to the power minus gamma. So let us take this out of integration because this doesn't depend on t1. So 0 to t prime dt1 e to the power 2 gamma t1, right? So v0 square e to the power minus gamma t plus t prime plus gamma over m square e to the power minus gamma t plus t prime 0 to t. Okay, so this will be, you can just check it once. So this will be e to the power 2 gamma t prime minus 1 v0 square e to the power minus gamma. So yeah, okay, so we can take this term common, v0 square minus gamma, 2 gamma will be down, 2 gamma m square e to the power minus gamma t plus t prime, and there will be one more term left, plus gamma over 2 small gamma m square e to the power minus gamma t, and this will be gone, so minus t prime. Yeah, so this is the average correlation Vt prime. Now again this term is 0, and if you have done this also, then you have obtained the same relation. This is 0 from the fluctuation dissipation, and this is gamma 2m square gamma to the power minus gamma t minus t prime. So we assume in this integration that t is greater than t prime. Let's say if t is less than t prime, then we would have got the reverse sign. So this will be just the mod of gamma over 2m small square small gamma e to the power minus gamma t minus t prime. Okay, so this is the expression for the velocity correlation in time. Okay, so now what we see that the velocity correlation decays exponentially with this mod of the 2 time t and t prime, and the decaying factor is this is coming from the drag. So our equation was m dv dt is equals to minus m gamma v, this is like depending on time, plus the noise term. So this has a dimension of time inverse. Okay, so this, if you plot this velocity correlation, so you will see that when t prime, so I am plotting t minus t prime on this axis, and the velocity correlation average on this, then you will see at when exponential is 0, means when t minus t prime is 0, this has some value, and then it decays exponentially, and the time scale over which it substantially decays is proportional to gamma inverse. So that there is an inherent time scale in the system which is coming due to the drag. Okay, and if you substitute the value of because we know that gamma, capital Gamma, is 2m small gamma kBt, so if you put that value, then you will see that this is nothing but kBt by m. Okay, since gamma over 2m square gamma is, so divided by 2m square gamma is kBt over m. Okay, yeah. So what we have seen, that this noise is not noise is delta correlated in time, because the collisions, the particles, small particles, fluid particles, they are bombarding at the time scale, let's say 10 to the power minus 9, or very low time scale, picoseconds, not 9 but picoseconds. They are hitting to the ball, big ball, or the big particle, or the Brownian particle, but we are not observing at that level, we are observing at much higher time scales. So the noise can be considered almost as delta correlated in time. So the drive property is delta correlated, but the driven thing has some memory, so it decays exponentially with the time lag. Now let us do some calculation. Before that, actually, we have to understand one thing, that this drag is coming, this drag m gamma is coming from the fluid viscosity. Okay, before doing that, let us first derive the expression for the diffusion coefficient for the diffusion of the Brownian molecules in the fluid. So let us define a displacement vector xt. So let's say if xt is the position or variable, or the position of the particle at time t, and let's say at 0 time it is at some x0, then the displacement vector, let us define it with capital Xt, is small xt minus x0. This is the displacement. And from the intuition, or you can derive it also, the mean displacement will again be 0. Just you can, so what is xt actually? Small xt is nothing but, xt minus x0 is nothing but 0 to t, because okay, so this dx by dt is vt. So what is this? If you integrate it, xt minus x0 integration vt prime 0 to t dt prime. Okay, since vt prime average is 0, so if you find out the average of the displacement vector, you will get 0. Now the interesting thing is to calculate the mean square displacement. Okay, so we want to find the average of the mean square displacement. So what is this? This is 0 to t dt1, 0 to t dt2, average of vt1 vt2. Okay, and we have derived this, that the correlation average is kBt by m and e to the power minus gamma t minus t prime. So let us substitute it here. So 0 to t dt1, 0 to t dt2 kBt over m e to the power minus gamma t minus t2. Okay, and so this is mod, right? So since all the things are symmetric in t1 and t2, if we replace t1 and t2, so the whole integration could be written as 2 times 0 to t dt1, 0 to t dt2 kBt over m e to the power minus gamma t1 minus t2. So then for this is for t1 greater than t2. If you do for t less than t2, t1 less than t2, you would have been you have got the same result. So we can just write twice of this t1 minus t2. Now just integrate it. So 2 0 to t dt1 kBt over m, and if you integrate it, what, oh yeah, there is, okay. So since we make it twice, so this will only go up to t1, because for the other half, so let's say this is our triangle, this is t1 axis, sorry, not triangle, this is our rectangle, t1 t2, and t1 is going up to t, t2 is going up to t, but we are integrating. Let's say we are starting t2 at 0, and when we reach t1, and we are just doing this half integration, right? The second part is the double of this, so we are just going up to t1 value. So the limit of this integration will be changed to t1. Okay, so kBt by m, and if you integrate it, what will you have? Integrating over minus gamma t1, and 1 over gamma will came down, so 1 over gamma e to the power gamma t1 minus 1. Okay, so we have 2 kBt over m gamma 0 to t dt1 1 minus e to the power minus gamma t1. Now let us do this integration. So we will have 2 kBt over m gamma, so this is t1 and t minus, so we will have minus 1 over gamma e to the power minus gamma t, oh not t1, t plus 1. Okay, so this is the mean square displacement of the Brownian particle. Okay, now we can see in 2 asymptotic limits. So since we have a time scale, so the average velocity correlation decays of the order of gamma inverse. So we can say that for gamma t, okay, so let me write it this way, 2 kBt over m gamma square gamma t minus or plus to the power minus gamma t plus 1. Okay. I'm doing some mistake, I guess, because because this minus 1 of gamma is here, so there will be a minus sign here. Okay, now this expression is correct. So this is the mean square displacement. Now you see two limits for gamma t tending to infinity. So in the gamma t tending to infinity, what we will let us look gamma t tending to 0 first. So what we can expand this exponential in that limit. So 2 kBt over m gamma square gamma t plus 1 minus gamma t plus gamma square t square by 2, and minus 1 is there, so this will be proportional to kBt over n t square x square 1. But for diffusion we have seen that the mean square displacement is proportional to the time itself. So at gamma t tending to 0, it is actually not the diffusion dominating motion, but it's like the individual particle is moving. This is actually termed as the ballistic part. So initially it has some ballistic kind of motion, and at the limit gamma t tending to infinity, so at t tending to infinity we will have this exponential term will be 0. So, and eventually the dominating term will be due to the linearity in time. So we will have 2 kBt over m gamma t. Okay. Now you can see this is something similar to our equation which we have obtained earlier. X squared t is equals to 2 dt. If you compare these two relation, this is for the diffusion of the molecular particles, like say dye or something else, diffusion equation or diffusion, and this d is the diffusion constant. So for our case this d is kBt over m gamma. So now we found the expression for the diffusion of the Brownian particle, which is kBt over m gamma. If you remember, the diffusion coefficient for the diffusion of the molecules, it is of the order of the molecular particles, or the atomic size was 1 over 2 L v bar, where L is the mean-free path, v is the average velocity of the molecules. In our case, this is actually related to temperature and the drag coefficient, and this drag is actually related to the molecular level by the viscosity of the fluid, because this has to be related, right? Because these bigger particles are moving in the sea of the smaller particles. Now we shall see that now we will actually see in some details that this gamma, what is the expression of this drag coefficient, how it is related to the fluid viscosity, and at last why we have derived all this, what is the importance of deriving this. Okay.